You know, it's probably one of the very first big questions we ever ask as kids. And if we're being honest, a lot of us never really get a straight answer. So let's change that. Today, we're diving into one of the most classic questions there is. Why is the sky blue?
And look, on the surface, it seems so simple, right? But the real answer is this beautiful mix of physics, the very air we're breathing right now, and even the biology of how our eyes work. It's a fantastic story.
And you know, Neil deGrasse Tyson put it perfectly with this quote. The idea is simple, but it has a few different parts that have to come together. So let's break them down piece by piece.
All right, so to really get this, we've got to look at the two main players in this whole story. First, the air all around us, our atmosphere. And second, the sunlight that has to travel through it to get to us.
So what exactly is our air made of? Well, it's almost all nitrogen and oxygen, but that tiny little 1%, that's where the magic happens. Because that's not just other gases, it's also loaded with all these microscopic particles. We're talking dust, pollen, soot, just tiny bits of stuff floating around. Keep those little particles in mind, they are absolutely key.
Okay, ingredient number 2, sunlight. And get this, we've been drawing it wrong our whole lives. The sun isn't really yellow. When it's high in the sky, its true color is a brilliant, pure white.
Yeah, that white light, it's not just white. It's actually a whole bundle of colors all smushed together. It's the entire rainbow. All the colors you see here, packed into a single beam. You have the longer, lazier waves of red and orange, and the shorter, more energetic waves of blue and violet.
All right, so we've got our air packed with particles, and we've got our sunlight packed with colors. Now let's see what happens when they actually meet. This is where the action is. So as that white sunlight barrels into our atmosphere, it starts bumping into all those gas molecules and tiny particles we mentioned. Now here's the deal. Those little particles, they're the perfect size to just mess with the shorter wavelengths of light, specifically blue light. They act like tiny little mirrors that don't absorb the blue light, but instead scatter it, sending it ricocheting in every single direction.
And this whole process, it's not just random. It has a super cool name, Rayleigh scattering. It's named for the physicist who figured all this out back in the 1800s, Lord Rayleigh. This is the science behind our blue sky.
So let's boil it all down. This is the crucial part. While most of the other colors, the reds, the yellows, the greens, mostly just pass straight through the air to our eyes, that blue light gets bounced around like a pinball. It's coming at you from every direction. So no matter where you look up, some of that scattered blue light is finishing its journey right in your eyeball. That's what paints the whole dome of the sky blue.
But what's so cool is that this one idea, this Rayleigh scattering, it doesn't just explain why the sky is blue at noon. Oh no. It also unlocks the reason for those fiery red sunsets, and even why the stars seem to just vanish every single morning.
Okay, think about it. At midday, the sun's pretty much directly overhead, so its light is taking the shortest possible path through the atmosphere to reach you. But at sunset, the sun is way down on the horizon. That light is now slicing through way more atmosphere to get you. And more atmosphere means more particles, and more particles means more scattering. So much of the blue light gets scattered away from your eyes that only the longer wavelengths, the reds and the oranges, are left to make it through, and that's your sunset.
All right, so that's sunsets. But what about the stars? I mean, they don't go anywhere during the day, so why can't we see them? The simple answer feels really obvious, doesn't it? The sun's just too bright.
But the obvious answer, that the sun is just too bright, well, it's actually wrong. Or at least, it's not the whole story. The real reason is once again our good friend, scattered blue light.
Get this, the sky itself is glowing. That scattered blue light turns our entire atmosphere into this giant, dim blue light bulb. This glow, this bright blue haze, is actually brighter than the faint little pinpricks of light from distant stars, so it just washes them out completely. If we didn't have an atmosphere, the sky would be pitch black, and you could see the stars clear as day right next to the sun.
And once you wrap your head around that our whole atmosphere glows, it leads to something, well, honestly, pretty profound about our home.
So let's talk about a number, 62 miles, or 100 kilometers. This is a really important number in aerospace. It's called the Kármán line.
And why that number? Well, that's the line. That's the altitude where the air gets so thin that there just aren't enough particles to do that scattering thing anymore. Once you go above 62 miles, the sky above you just turns black. The blue glow is gone.
And this really puts it all into perspective.
62 miles might sound high, but compared to the size of the Earth, wow, this analogy is just perfect. The layer of air that gives us our blue sky, the layer that supports all life, is proportionally just as thin as the skin on an apple. And that right there, that's the real gut punch from this whole thing. The very process that gives us our beautiful blue sky, it reveals that our life support system is just this incredibly thin, frail, fragile layer. It's not some vast, endless ocean of air. It's a delicate film.
So we started with a simple kid's question, right? Why is the sky blue? And it took us on this incredible journey through physics, all the way to this profound truth about our planet. Knowing this, knowing our atmosphere is as thin and delicate as an apple's skin, the next question we have to ask isn't about science at all. It's about us. What are we going to do to protect it?